Now that we have given certain minimal insight, certain physical insight to those vector operators, the curl and the divergence, let's see what they tell us in the context of Maxwell equations. For that, we're going to start with Gauss laws. Remember that Gauss law for the electric field, it's given by the divergence of D is rho, where rho is the charge density. Now, if we take volume integral in both sides, we have this expression, but it is clear that the volume integral of the charge density is the total charge that we have inside that volume. On the other hand, if we apply the divergence theorem we had just seen before, we can write this equation. But notice that this integral is just the net flux, or the net flow of D over the surface S. So, what Gauss law is telling us is that the net flux of D over a closed surface equals the total electric charge inside that volume. So, the end is something that it's expressing in a mathematical way some very fundamental relationship that there is between charge and the electric field. Equivalently, for the magnetic field, we have that flow of B, it's always zero. Why is that? Well, it's always zero because there are no magnetic charges in nature. So since we don't have magnetic charges, always the net flow of B over a closed surface has to be zero because we'll never find magnetic charges. Remember that Maxwell equations at the end are derived to explain certain experiments that have been observed in nature. And since always we have never found magnetic charges, always B, it's of the magnetic field is solenoidal. Its divergence is always zero. If we try to find similar reasoning for Ampere's law, this is Ampere's law, and in that case we're going to take the surface integral in both sides. Now, in this case, notice that this surface integral of the current density over a surface just is giving us the total current that is crossing that surface S. So we can write, and using the Stokes theorem, we can write this expression. This is the circulation of H, and this is the current, and then we have that term here. Now, if we consider the electrostatic case, in an electrostatic case it means that the fields do not change with time, then the time derivative of D is zero, so the previous expression becomes this one. Now, because of the symmetry of the problem, we have a certain current, but because of the symmetry of the problem, we can understand that the magnetic field along this path will be constant, so we can write this relationship. The total current will be that constant field, and then 2 pi r, which is just the length of this integration path. If we remember the relationship that we have between the field intensity vector and B, we can write this expression, which is a very well-known expression for the magnetic field produced by a DC current. And we can see that this is directly derived by Ampere's law. What happens in the electrodynamic case? Imagine the case in which the time derivative of D is not equal to zero. So for that, imagine that I have a wire with a certain current, and here we have a parallel plate capacitor. We know that between those two plates there will be an electric field, and if we are with a time varying field, that field will change with time. Now, what happens if we apply Ampere's law in this path C1? Well, we are in a similar case, similar to the previous case, and if we apply in C2, now in that case we don't have a current here because there is that gap caused by the capacitor, but we have a time varying electric field. If we look at those two expressions, we see that actually the current I and this term here, that time derivative of the electric field, actually play a very similar role, and this is why this term is called displacement current. It's analogous to a current. It's not caused by the movement of charges, but it's caused by that time varying field. And at the end, it's that term that explains why we have current flow through a capacitor. And we only have it, and we don't have it in DC. If we only have a DC current, we don't have that current flow.